where the Klein-Emscher flows into the Rhine, in Duisburg-Walsum, there is a place that was closed to the public for generations. 4 hectares of former coal mining and water management land, shaped by pitworks, tunnels, and the old pumping stations that once controlled these waters. As part of the Emscher naturalization, this industrial site is being reopened as a naturalistic landscape park under a single guiding title, the Green Window to the Rhine. And at its heart stands a new bridge. The task was demanding. A 50-meter pedestrian and cycle bridge had to close the last gap in the public path network and cross the reopened river mouth without a single support standing in the water. It had to touch the water, the soil, and the mature trees as lightly as possible. It had to last with minimal maintenance, and it had to give this transforming region a form with genuine identity. The answer begins by breaking with the grid. The straight, Cartesian lines of classical engineering are set aside. First, the entire site was captured as a millimeter-accurate digital twin, laser scanned and drone mapped into a dense point cloud, precise enough to place every foundation clear of all roots and protected ground. On that foundation, a generative, AI-driven process let the structure grow. Using evolutionary algorithms, generative AI and topology optimization, the system ran a continuous loop: set up, generate, explore, adjust, validate, producing hundreds of structural variants from a few precise rules, where it could build, where it could not, and how the forces had to flow. Material was placed only along those forces. Form follows force. From more than 120 final iterations, one form emerged: asymmetric, flowing, a hybrid truss that looks less designed than grown. Every member was tested. Finite element simulation mapped the stresses across the whole structure: red where forces run high, blue where they fall away. The wall thickness of the main tubes was then tuned to that map, thickened where the loads demand it, thinned to almost nothing where they don't. The result is a structure that carries its loads with the least possible material. At its core, this is a continuous four-span girder, just under 50 meters long. But the true innovation lies in the joints. At the 6 most complex connections, where struts meet pylons at impossible angles, conventional welding reached its limit. So these nodes were not welded at all. They were printed, built up layer by robotic arms, in stainless steel, through directed energy deposition. Each node replaces a cluster of fatigue-prone welds with a single, flowing, organic transition, one piece of metal, grown to follow the forces passing through it. The same technology shapes the organic railing posts along the walkway. Because additively manufactured steel is not yet covered by German building codes, this bridge required something no German bridge had received before: an individual structural approval and a project-specific construction method approval from the highest building authority in North Rhine-Westphalia. To earn it, the printed nodes went through an exhaustive testing program at the KIT Institute for Steel, Wood, and Stone. Tensile tests, impact tests down to -30 degrees, computed tomography, and micrographs, all proving a dense, void-free, fully bonded material. Only then could it be built. This bridge stands in the floodplain of the Rhine. It is designed to survive a 100-year flood that submerges the entire truss. The engineers modeled the pressure of water flowing at 3 meters per second, the buoyancy of the hollow steel tubes held down by anchors at the abutments and the pylon feet, and even the impact of a 200-kilogram tree trunk carried by the current. Open and permeable, the truss lets the forces pass through and channels their energy safely into the ground. The whole structure floats on elastomer bearings that absorb movement and temperature without strain. The walking surface is made of recycled, weather-resistant panels, and directly above the printed nodes, transparent fields of laminated glass are set into the deck so that everyone who crosses can look down and see the technology that carries them. To protect this fragile landscape, almost the entire bridge was built in the workshop, then divided into 4 transportable segments. On site, a 300-ton crane first raised the 3 pylons into their precise, lean positions. Then, segment by segment, from north to south, the truss was lifted into place, fine adjusted by hydraulic presses, bolted, and welded. The joints were tucked discreetly behind the pylons, so the flowing form reads as one continuous line. At its core, this is a continuous 4-span girder, just under 50 meters long, built as a spatial tubular truss from hot-finished round steel. The loads travel through 2 concrete abutments and 3 inclined, Mikado-like steel pylons. The main tubes measure 219 millimeters across. Their walls graded from 5 millimeters up to as much as 30 at the most heavily loaded joints. The pylons stand on deep caisson foundations that reach down to the load-bearing brine sands, carrying the horizontal forces of wind and current safely into the ground. What stands here now is more than a way across the water. It is one of the first bridges of its kind in Germany, designed by algorithms, printed at its joints, and approved on new legal ground. With its branching form and warm, rust-red tones, it settles into the recovering landscape and opens a place that was sealed off for generations. A structure grown from data and steel, and a visible sign of a region remaking itself.